Hey everybody, so in this video I want to talk about something that is not widely known but is more and more known. I see more and more people talking about it, and I'm going to talk about it from my perspective and in my world. And then how I come about this, and in my perspective and my world, this is a mathematics and a physics problem. So the big underlying hypothesis, and I'm going to prove it out for you very directly within this video, is that audio and images share the same mathematics, the same manifold, and essentially the same underlying latent space that they operate within and navigate within. That's both good and bad overall, because essentially what that does and means is that this is additional noise that the model can pick up on, but if we alleviate that and we account for it, then the model can utilize this additional noise as additional data, and we can essentially function and smooth out both video, image, and audio generation by simply knowing these things overall. Sorry. And then so that leads us to the big question, which is, why do AI models seem to understand both pictures and sounds with the same kind of math? And then this project is built around a simple but powerful idea that images and audio live on the exact same hidden structure, a shared manifold. So first of all, what's a manifold? Think of a manifold as a shape that data lives on. Imagine a crumpled up piece of paper. From far away, it looks messy, but up close, you can still walk on it as if it were flat. In AI, data like images or sounds may look very different, but they can unfold onto the same kind of hidden shape. So this is what scientists mean when they say the data lies on a low-dimensional manifold, and we'll dive very specifically into low-dimensional manifolds. So what exactly is latent space? AI systems don't see the world like we do. Instead of raw pixels or sound waves, they compress everything into latent space, a hidden representation where similar things cluster together. So a picture of 5 and the sound of someone saying 5 both land near each other in latent space. Latent space is like a map of meaning that different senses can share. This brings us to the Hilbert Curve, which we're going to talk about or utilize very extensively within the mathematics for this model. So the Hilbert Curve, drawing a line through a picture. Here's the trick we use in this notebook, which is we turn an image into something that looks like audio. A Hilbert curve is a clever squiggly path that passes through every pixel in an image exactly once. If you follow that path and record pixel brightness as a wave, you suddenly have something that looks just like a sound waveform. The magic, the Hilbert curve, preserves neighborhoods. Pixels that are close in the picture stay close in the wave. So in a sense, we play the image like music. So within this concept, just to visualize this particular concept a little bit better, if you're familiar, I forget the exact name for it, but so within chess, there's it creates a cool pattern, right? Where you can, it's like the knight's journey, like where you move the knight exactly once on every single square, right? Where it can never touch a square that it's already been on. This is essentially kind of that same type of concept within the a one-dimensional latent space. If you do that, you get a waveform, and then so that's what we're going to play around with. And then so why does this matter? If an image can be turned into audio without losing information, then both are just different views of the same geometry. By comparing these views, we can show that AI can align them in a shared latent space. This is more than just a fun trick. It's evidence that vision and hearing are not separate silos. They're connected through the same mathematics. This is deeply important on the physics level because it ties essentially to computational theory in that regard, right? Which is why I'm interested in it and my focus in it on that level, right? And the fact that if computational theory is true, then being able to do things like this would be true overall. And then so here we are, right? Essentially, the medium of the information and the data doesn't matter. It would be purely and 100% transferable. It's just data. It's all waveforms at the end of the day, right? So what you'll see within this notebook, we're going to take an image, we're going to convert it to audio, and then we're going to convert that audio back into an image. So it's going to make a full round trip, and we're going to prove that Hilbert mapping preserves the entire structure of all of them. We're going to utilize this, and we're going to measure this via metrics, and then I'm going to showcase it to you as well. We're going to utilize shared features via canonical correlation analysis, or CCA, revealing dimensions common to both audio and image. And then we'll utilize cross-modal retrieval tests to find the right image from sound and vice versa, beating random chance. So, big picture here. This is a first step towards a bold claim. All sensory data may be a different languages describing the same hidden shape of reality. AI models don't just learn pictures of sound separately, they learn the geometry of information itself. The geometry is the shared manifold. Why does this matter overall? Big reason why this matters overall is very simplistically and very straightforward, because of the fact that what we're looking at here and what we're examining is currently a big problem within video, right? Like image generation, audio, and video, like everything that is around these things, understanding exactly how the model reads, views, understands, looks at these data sets overall, and then what the missing element within that is that a lot of people don't understand is that there's an audio signal that is within and can be recognized by these AI models within every single image, right? And then whether or not like that's human detectable or not doesn't matter when you're dealing with an AI that can detect that, right? It's like look at it like, for example, like the color spectrum, right? Where humans can see very narrowly on that color spectrum overall, but of course there's a broad amount of colors and a light that exists outside of that we don't see, right? And so that's kind of this same exact concept. So when you're looking at an image, there's sound data that is outside of the image that we just can't see, but the AI models can see. And then so if you don't account for that and you don't say, hey, we know that this exists, the model is prone to overfit to that data, etc., right? And then so that's kind of what happens. So in this particular notebook here, this notebook demonstrates in a hands-on and a visual way that images and audio share latent manifolds. We use a simple but powerful pipeline, Hilbert Curve mapping, round-trip reconstruction, feature extraction, shared latent alignment, cross-modal retrieval, and metrics and visualizations. So why this matters? This shows that the same geometric and spectral properties can encode both images and audio. It provides a reproducible, minimal example for teaching or research, and it opens the door to exploring a unified latent space for multiple modalities. And then so essentially here you can configure and tweak the parameters, and then so you can tweak the output directory, number of samples, the sample rate, and then the data set. In this instance we're utilizing MNIST digits. And then so here's all of the code. You can see it's a bunch of Hilbert transforms, right? And then so it's like a bunch of math there. Going through, you have your data sets, your baselines, your actual Hilbert transform, mapping the Hilbert transforms, because we're doing it from, again, we're taking, I'll show you exactly what we're doing down here. It's probably the simplest way. So here's all of our metrics, here's all of our correlations, etc., like all good stuff here that we want to see. Hilbert transforms are very nice within that. And then so this is our data, right? And then so this is the original data set. So it's MNIST digits, so 5041, and then we convert this to audio and then back into image, right? And then so here's the original and then it converted from audio back into image. And then at this point, you might be saying, hey, where's the audio? And that would be a very straightforward question to ask. And then so when we look here, I forget how Colab works overall within this. When we looked here, there would be a file output which had our files within this. Lucky for me, I do actually have a few of those files downloaded. So we can take a look here, right? And then so here's audio for 2 of these images. That's it here. That's sample 7. Sample 1 is it's different. Or sample 0 here. So this is the this is the audio for 0. This is the audio for the digit 7, right? Like exactly here. And then so it gets converted back from that into a number, and then that audio is extracted from this image, right? And then the audio that is the main point of this overall is that audio that is extracted from these images is unique to each one of these images. The audio that is extracted from this image of 5 is different than the audio that is extracted from the image of 0, then it's different than the audio that's extracted from the image of 4, etc. Right? And then again, not different to you, not different to like human perceptible. Human's not going to detect that, but an AI model that is running through these things is going to detect that. Like that's exactly what it's trained to detect, right? And then so knowing that that detection is in existence and within play there gives you significant ground and improvement when it comes to training these models, and it puts you like on a whole different universe when it comes to training these models overall, right? I guess that's the biggest thing to end within this, right? Is like people ask me like, how do you get into and build your sort of like understanding around these things, mentality, etc., right? And it's all about just being immersed in these things, and then understanding understanding to me like the different physics elements of it, right? And then when you understand the deep physics behind a lot of these things, and it's just certain things start to click once you understand, and you can't shortcut like deep physics knowledge within these things, right? Like you could speed run AI knowledge, and then you could put yourself out there as like a half-baked like AI. I see that, like that's what a lot of people do, right? But the underlying core within that is very much driven by understanding the math and the physics very intimately behind these things. And then for me personally, like I've just happened to be studying like physics, especially like my entire life around these things. And then so but the best place to start is understanding and stacking on that knowledge here, and then hopefully that's what this video does for you and provides for you within this overall. And then so I'll leave a link to both this notebook here as well as the document that I went over here. And if you like this type of content, please like and subscribe. Thank you very much.